for presentation 3.3. It's called Organizing for Success. And you see an indication that's the perfect place for you to study. No, not quite. It says science is organized knowledge, wisdom is an organized life. That's a famous philosopher by the name of Immanuel Kant. So the first thing we want to do is look at our goals. And the goals are that the students will understand the relationship between period and the atomic structure, the relationship between columns and atomic structure, and become familiar with the properties of the various chemical families. So let's look at what we know. We know that the model of the atom has developed over time. We know that atoms can vary in protons, neutrons, and electrons. We know that protons and neutrons are in the nucleus, and we know that electrons move around the nucleus in a larger volume. So this is what we know about the atom. This is what we learned in the lab. We learned that the periodic table has an interesting shape, and that there are similarities in the columns and rows of the periodic table, and that the periodic table can be very, very useful if we know how to use it effectively. So now let's look at the history of the periodic table. This guy right here, this is Mendeleev. Mendeleev is a Russian chemist who was the first one to come up with a systematic way of organizing the elements. And what he did is he organized the elements by mass. And he noticed that when he organized them a certain way by mass, he could line them up and they had similar chemical properties. So in other words, these elements all had similar chemical properties. These elements all had similar chemical properties. And it was an interesting thing. Mendeleev was so confident in his periodic table that whenever he came across something that they didn't have an element for, he actually left a gap and said, there will be an element that will be discovered, and when it is, it'll go there. So Mendeleev was kind of the father of the periodic table as an organizational system. Now, Mendeleev's periodic table is not the one that we currently use because of isotopes. Now, we've already talked about isotopes and the fact that atoms can have different numbers of neutrons. Well, if you have different numbers of neutrons, that actually changes the atomic mass, and then it changes its position on the periodic table. So we use what is called the modern periodic table, which was created by Moseley. Now, this guy right here is Moseley, and Moseley came up with a system that addressed the inconsistencies in Mendeleev's periodic table by organizing the periodic table based on the number of protons, which we call atomic number, but the number of protons. When you do this, the same periodic trends come about, but there are no inconsistencies. And also, you have the similar chemical properties, and he was able to fill in some of those gaps from those missing elements. You should bookmark this site. This is a screenshot of ptable.com. It comes with the information of what the elements are, what their atomic masses are. It's a traditional periodic table, but it also includes electronegativity and electron affinity and ionization energy, things that you don't know about yet, but we will address later in this year. So it's a great site for you to have as a reference. Chemical periods. Chemical periods are defined as the rows of the periodic table. So everything that's in this top row is defined as the first chemical period. Everything that's defined in the second row is the second chemical period. And it turns out this actually references the energy level of the electrons that we talked about in the Bohr atom. Now we're going to go into more detail of that later, but the fact that you have the first orbit references the first chemical period. The second orbit references the second chemical period, and so on and so on and so on down the way. So elements in the same period have similar energies for their electrons. So an electron in this third orbital, an electron in this third orbital have very similar energies, but they're very different from the one in the first orbital. So that's what we have for chemical period. Chemical families, on the other hand, are defined by the columns. So when you have the columns of the periodic table, that's what we talk about chemical families. Elements that are in the same column have the same outer electron structure. Now we're going to get into that later, but that is the reason why they have similar properties, is they have a similar electron structure. So because they are similar electron structure, they have similar periods. So fluorine acts very similarly to chlorine, which acts very similar to bromine, whereas lithium acts very different from fluorine, even though they're in the same chemical period number 2. Okay, even though they're in the same chemical period, they have very different properties. But lithium acts very similarly to potassium. So the chemical families, the vertical columns, will tell you how they react. So the first one says, which chemical row, 1, 2, 3, 4, 5, is likely to have the greatest number of electron levels? And we addressed this. We said that when you go 1, 2, 3, 4, 5, as you go down the periodic table, you're adding rows. So in the first one, you only have the first row. In the second one, you have the first row and the second row. In the third one, you have the first, second, and third, and so on. So of these, 5 is the one most likely to have the greatest number of electron levels. Next, find the chemical, row, and family number for titanium on your periodic table. You should be able to do that on your own. I will reference that titanium is Ti, and you should be able to find its location, figure out what row it's on, and figure out its chemical family. In other words, which column is it in. Finally, later this year, we will study valence electrons, or electrons in the last energy level. The number of valence electrons determines what type of chemical reactions occur. Are valence electrons linked to families or periods? It turns out valence electrons determine the reactivity. So when they're talking about the reactivity, that is referencing the family. So that's vertical rows. Next, we need to address the different types of chemical families that they actually are and some of the properties. The first one you have are alkali metals. Alkali metals are in group 1. They tend to be soft, which means they're metals that can actually be cut with a butter knife. They're metallic, in other words, they're shiny, they look like metal. They tend to be lustrous, which means that they're shiny, and they're the most reactive. If you were to drop something like cesium or pure sodium in water, it would explode. Next, you have the alkaline earth metals. That's group 2. Which is in the second column that we have here. Includes things like calcium and those sorts of things. They're soft as well. They are also metallic, but they tend to be dull. They tend to not be lustrous. They're not bright and shiny like you traditionally think metal to be. And they are also reactive, but they're not nearly as reactive as you would see with the alkali metals. And they're not going to explode when you put them in water, but they will definitely react. Next, you have the transition metals. The transition metals occupy this entire group right here. See how it's lowered from the periodic table? It creates like a little bowl. These elements right here are called the transition metals. They're groups 3 to 11. They're hard, which means they're very difficult for you to actually cut. They're metallic, they're shiny, they're lustrous, they're colored in solution. So whenever you put it in water, they tend to change the color of the water. Copper turns something blue, iron turns it red or orange. It kind of depends on what it's mixed with, but they do change colors. And there are conductors of electricity and heat. Finally, you have the lanthanides and actinides. They're the weird ones that are kind of pulled out from the periodic table, and we'll talk a little bit more about that when we talk about electron structure. But they're pulled out and put at the bottom of the periodic table because they're in what's called the F block. They tend to be silver/white, kind of a mixture. They tend to be fairly soft. They're very reactive, but they tend to be more reactive in kind of nuclear reactions because they're not very stable. They tend to do things like burn in air. And they're what's called paramagnetic, which means they can be made into magnets relatively easily. Then you have halogens. Halogens are in group 17. They're gases at room temperature. They tend to be highly reactive, especially for nonmetals. If you were to put an alkali metal and a halogen, they react very quickly with one another. They're highly reactive with other nonmetals as well, and they tend to be lethal for the most part. You can't really be exposed to a large amount of chlorine gas or fluorine gas without having some significant health problems. And they're in group 17 right here. And finally, you have group 18. Group 18 tend to be gases. They're all gases. They're called the noble gases. They're non-reactive. That's what really makes them known as they're non-reactive. And they tend to be gases at room temperature. There are also other groups, group 16, group 13, 14, 15, and 16 we didn't really address. Group 16 is sometimes called the chalcogens, but generally they're referred to by number. So group 13, group 14, group 15, group 16. So we come to some example questions. It says color in the 2 most reactive chemical families. The 2 most reactive are the first, which is the alkali metals, and the second to the last, which is the halogens. Okay, those are the ones that tend to be the most reactive. The least reactive are the noble gases. Proficient. It says scientists discover a box containing an unknown sample of gas in the back of a derelict building. The scientist attempts to react the gas to help determine its identity, but the sample fails to react. What chemical family does the sample most likely belong to? Now, remember, as far as a chemical property is concerned, the fact that it does not react implies that it is a noble gas. Now, you wouldn't be able to say which of the noble gases it is at this point. You could do further tests in order to say what they are, but the fact that it's non-reactive would indicate that it is a noble gas. And finally, A student is investigating a sample of unknown material. The sample is highly reactive. What tests could be done to determine if the sample is an alkali metal or a halogen? So you have to compare the properties of these two. A couple of things right off the bat is alkali metals tend to be solid, while halogens tend to be gases or liquids. So that would be the first test that I would go to. If it's a higher temperature that's actually melted the alkali metal or the halogen, and you can't tell if it's a gas or liquid, the next thing you could do is you could actually run it through and you could see, is it positively or negatively charged. Alkali metals tend to be positively charged. Okay, these halogens tend to be negatively charged. That's another test that you could do. So there's lots of options that you have. Another one that you could do that you're probably not familiar with yet is you can actually add both of them to water to make solutions, and these alkali metals tend to make bases, and this halogen tend to make acids. So there's lots of tests that you could do based on the fact that they are in different columns.